start.
Hello, everyone. Welcome to the Illinois Tech Social Sciences Great Problems, Great Minds seminar series. For today's seminar, you can submit questions during the webinar by typing in the chat box. We will open the floor to questions at the end of the webinar. Today's speaker is Professor Liang Mao. Dr. Mao is an associate professor in the Department of Geography at the University of Florida. He received his PhD degree in geography at the State University of New York at Buffalo. He is now teaching and research in medical health geography. His research aims to offer better understanding on the human disease system with geospatial approaches and technologies, specifically focused on agent-based modeling and simulation, geospatial network analysis, spatial accessibility, and disparities. His research has been supported by National Research Council Transportation Research Board, NSF of China, and others. He has published more than 15 articles widely on topics related to medical health geography, agent-based modeling, geospatial network analysis, and accessibility and disparities in top journals such as computers, environment, and urban systems. The Annals of Association of American Geographers in the Health and Places. It's very delightful to welcome Dr. Liang Mao.
Thanks for your introduction, and it's great to be here to present. So today I would like to take this opportunity to talk about our recent research on mobile phone geography and precision health or precision public health. So all the studies were accomplished by UF Geography in collaboration with Shenzhen Institute of Advanced Technology and also Shenzhen CDC. Okay. So what is precision public health, or also called precision medicine? It was a new concept in public health proposed around year 2015. It argues that the one-size-fits-all treatment or intervention might not be effective. Instead, it recommends a personalized treatment or prevention based on individuals' unique traits such as their genomics, their behavior, their health records, even their social media activities. So, so in such a way, while they believe that the cost effectiveness can be optimized. So simply speaking, the precision medicine or precision public health is a concept of giving the right treatments or intervention at the right time to the right person or right people. So you may hear some commercials saying like we are not treating you as an ID number. Instead, we treat you as a real person. So yes, that is concept of precision health or precision medicine. Now we studied many literature about precision public health, and we found that most of the personalized intervention or treatments have been focused on individuals' genomics, their physiological and social ecological characteristics. However, we think while few studies have considered people's individuals' spatial temporal behavior pattern, and possibly because they don't have enough data to describe people's travel behavior. So on the other hand, we think the mobile phone tracking might help us to fill this gap, because it covers a large population and also offer very detailed information about how people are actually moving over space and time. So our research tried to explore how to use the mobile phone tracking technology and also data sets to better inform the precision public health for disease control. So just give you some background about mobile phone tracking technology. So mobile phones can be tracked based on a network of cell phone towers. So let me see, can have a pointer here. Yeah, so these are the mobile phone cell towers, and each tower has a coverage area, and we call them CA. That is often approximated by a Thiessen polygon. So if you have learned GIS before, and a key feature of Thiessen polygon is any location within this polygon is closer to the central tower than to any other towers in the study area. So a cell phone is connected to a cell phone tower when entering its coverage area. And then the cell phone will get the geographical coordinates of the cell tower. So this is one example of how we track the hourly travel behavior of one case or one mobile phone user. So we have the user's ID, and also we have the record of each hour from 1 to 24 in a day. And we have the geographic coordinates of every hour. So these coordinates are actually cell phone tower's location. It's not exactly location of that mobile phone user. All right, so from the mobile phone tracking records, we can retrieve a movement trajectory for every mobile phone user, something like this. All right, so here the XY axis represents a geographic space, and the Z axis is the time. All right, so this is the movement trajectory of one mobile phone user. So you can see this person stay at location A for, let's say, a few hours. And the green circles here are the mobile phone stops being recorded in our data set. So this guy stops, stay at location A for a few hours, and then start to travel to location B, and then another location, and then travel to location C. After that, this person stay there for another few hours, and after that, going back to location A. So based on this travel trajectory, we can also infer actually where they possibly live and where they possibly work based on the visiting frequency and also how long they stay there. For example, if one mobile phone user stay at a location, let's say from 9 p.m. to 6 a.m. and very frequently, let's say every day, and that means, well, that location is very likely to be the home location of this person. Or if a mobile phone user stay at a location frequently between 9 a.m. to 6 p.m. or 5 p.m., and that location is very likely to be the workplace location for that person. So that's some background about mobile phone tracking. So I'm going to move on to the first case study I would like to talk about. We are trying to use the big mobile phone data sets to map the transmission risk of dengue fever in the urbanized area. So our studies area is the Shenzhen city, which in the South China. It's a huge city with a population about 13 million. And so the dengue fever is a mosquito-borne disease, and it's characterized by an acute onset of high body temperature about 3 to 4 days after mosquito bites. All right. So between August and October of year 2014, there was a huge outbreak with about 500 cases in the city. So that's why the city government want to scale up their control efforts for the future outbreaks. But the problem is they don't know where the transmission risk is high. So that's why they asked us to do this kind of research, trying to map out the transmission risk of dengue fever across the city. And we did this at the level of cell phone tower coverage area. So basically, we're going to estimate the transmission risks for each polygon in the city. We consider two types of transmission risk. One is called the local transmission risk, which is caused by mosquito bites. However, mosquito can only fly a very short range, for example, from 500 or from 50 to 100 meters. So they can only spread disease locally. Well, it is our human travel that actually caused the wide dispersion of disease spread in a city. Right? So, for example, here a person was bitten by an infected mosquito, and then this person can travel from home and carry disease to the workplace or shopping mall or grocery stores, and then infect mosquitoes there. Right. So, I mean, so it's necessary to estimate the risk of importation by human travels. Right. So that is where our mobile phone geography or mobile phone tracking data set contributes. All right, so the data sets we obtained is from a local mobile phone company, which has about 75% market sharing in that city. We got 5.85 million users, and we have the hourly records of their location in a very typical day in year 2012. So you can see this map basically shows the hourly movements of those mobile phone users between cell phone tower areas. So we start with estimate local risk estimation. So the risk caused by mosquitoes only. We have 300 local cases confirmed by the local CDC. And also it creates 7,500 background points as a reference. We consider 12 predictive variables, for example, temperature, precipitation, elevation, distance to water, population density, road network density, and so forth, so on. And we use a random forest classification, which is a machine learning process to grow a classification tree based on randomly sample the data sets. Right, so we did some model validation to make sure that our model predictive error is under 5%. And then we also find that temperature and precipitation and the road network density are the most important factors to predict the local risk. So then we use the model to predict the local risk of dengue transmission in a raster grid with a spatial resolution of 100 meters. So this is our estimation from the random classification model. So this is the dengue risk map if we do not consider people traveling. So as you can see, there is a notably higher risk cluster in the southwestern part of the city. And there's another high risk area in the north central part of the city. And then we start to add human mobility into our risk estimation. So we calculate the probability of a mobile phone user acquiring dengue fever for 24 hours using the formula below. So as you can see, it's a function of both space and time. All right. So for every hour, so from hour 1 to hour 24 in a day, any mobile phone user I can travel to a different location and then exposed to a different local risk of infection, which is denoted as the RLT. And also this probability is augmented by the activity level of mosquitoes over time. Right. So as you can see from this curve, the mosquitoes are most active in the dawn and also the dusk. Right. So we consider this time period as well. So that's the individual probability of getting disease. But there is an uncertainty issue because, well, as I just mentioned, the mobile phone user enter into the coverage area of a cell phone tower. We only has the location of the cell phone tower. So basically, this mobile phone user can be anywhere in this polygon, but we don't know where this person is. So that's the that is the uncertainty. So to account for it, we calculate the probability for 1,000 times by randomly sampling the local risk within the coverage area. So that's the randomness, or that's the uncertainty in our estimation. So finally, the total importation risk for any cell tower's coverage area is the sum of the infection probabilities of all visitors. So if, let's say, if a coverage area has 100 visitors, and then the total importation risk into this coverage area is the sum of the probabilities of all 100 visitors. And then we get this map. Right, so each polygon is a coverage area of a cell phone tower. And so the red color means there's high risk of importation, and green color means, well, there's actually lower risk of importation. So still we have a large cluster of high importation risk in the southwestern corner of the city. So how about uncertainty for those high risk areas? So we map out the top, the coverage areas of with the highest importation risk, the top 50. And also we look at the coverage areas with the top uncertainty, which is actually measured by the mean of mean value over the standard deviation from the 1,000 randomizations. Right. So fortunately, if you can see, well, those high risk areas do not overlap with the highly uncertain areas. Right. So this is actually the map we are going to provide to the government for intervention. So these are the high risk areas. They need to consider some control efforts. And while this first study also led to our second study about how to control the importation risk in the city. So if you look at this formula, which we use to calculate the individual's probability of getting infected, well, if we change, or if we can suggest them to avoid the high risk area and also avoid the peak hours of mosquitoes, and we can reduce their chance of getting infected, and thus we can also lower down the importation risk. And such change of travel behavior can possibly be made by sending those people some personalized short message. So that's basically our second study, which was published in year 2020. So the usage of the short message service is not new. It's already a part of people's daily life, and also it's a powerful tool in public health in order to, let's say, spread knowledge about health, like HIV transmission, or being used to promote health behavior like washing hands, wear face masks, and also be used to actually remind patients to take medicine, or alert people about imminent risks like extreme weather, like crime. But we find that few messages or few applications have been designed based on individuals' spatial temporal travel behavior. So in this second study, we proposed a set of short message policies and tailored based on individuals' travel behavior. So this is where the mobile phone data can contribute. And also we try to evaluate the cost effectiveness of those policies. Excuse me. So we're trying to focus on the coverage areas with the highest importation risk. And we find that there were a total of 310,000 mobile phone users who had visited these red areas. And so those mobile phone users will be actually our targets for short messages to change their travel behavior. So we devised 3 groups of short message policies. The first group is called spatially targeting short messages, so which only ask people to avoid their trips to high risk areas. and alter their trips to low-risk areas. So for example, the spatial policy one can be would send people following message. So let's say due to dengue fever outbreak recently, please consider canceling all your trips today to following high risk areas, blah, blah, blah. And instead, you could replan your trips to following low risk areas, blah, blah, blah. And then the spatial policy two is less restrictive. So it says, well, please cancel your discretional trips, not all trips, like shopping and banking to the high risk areas. And instead, you could replan your trips to following low risk areas, blah, blah, blah. So this kind of policies only change people's spatial location of their destinations, but no change on their time. So which means they are supposed to reach the alternative destinations in a low risk area at the same hour as they planned. So that's why it's called spatially targeting message. Of course, we have another group of message which is called temporally targeting message. So which only asks people to change their travel time to avoid the peak hours of mosquitoes, but there's no change on their spatial destinations. So if you look at this chart here, the blue curves is the mosquito activity level over 24 hours. And the orange curve is the human activity level. So there are two major overlaps, one from 7 to 8, the other from hour 18 to 20. So during which both activities level, both activity levels are high. So our temporary policy could send people messages, something like this. So due to the dengue fever outbreak, please adjust your departure or arrival time to a specific hour to avoid mosquito biting peak time. So for example, if a user left home before 8 o'clock in the morning, so we could send this person a message to say, please leave home after 8 o'clock to avoid mosquito bites peak hour. Or if someone returned to home after 18, which is basically 6 p.m., and then we can send this person a message ahead and saying that please return home before hour 18. So trying to change their temporal pattern of behavior. Well, the last group is to combine the intervention on both space and time. So we call spatial temporally targeting messages. So which ask people to cancel certain trips within a specific time period so that their travel trajectories change in both space and time. So the first policy called ST1P is to basically ask people to consider stay at home from hour 18 to hour 10. So which are the peak hours of mosquito bites. And the second policy is the most aggressive one. So we just ask people to stay at home for all day long. All right. So we have a number of messages policies, and we know that not everyone will comply with the travel suggestions. So we simulate different compliance level from 10% compliance to 100% compliance, which is shown as here. So basically, the animation shows the policy effectiveness under different level of compliance. We calculate the risk reduction ratio to measure the effectiveness. So it's basically the relative change of importation risks for each coverage area before and after the policy is implemented or the messages are sent. So basically blues, if you have a negative ratio, that means the risk is reduced and they are displayed as blue, and vice versa. If you have positive ratio, that means the risk is increased and they are displayed as red. So, I mean, you can see it's not all the policies can redistribute the transmission risks in our study area. And it's not surprising that some areas got reduction in the in the risk of transmission. But also you can see there are some red polygons as well, which means well these areas did have some increase in their transmission risk. So how come? So we think this might because that when people reroute their destinations to low risk areas, and then they may also introduce to diseases, introduce diseases to those areas, which leads to an increase of risk. So we look at the overall effectiveness of those policies in the entire study area by averaging the risk reduction ratio for all high risk areas by policy. So each curve stands for policy, and also by different compliance level. So as you can see, the spatial temporal policy 2 is the most effective one because it gives you the highest reduction ratio, but it's also a very aggressive one. It asks people to stay at home for all day. And the one follow it is the SP2, the spatially targeted policy number 1, which only suggests people to cancel their all trips to high risk areas. And the temporal targeting policy, which only asks people to change their departure and arrival time, is the least effective strategy. Right, so but when we look at the policies, we also need to evaluate the costs. So here we looked at 2 indicators to measure the cost of different policies. So one indicator is the risk reduction per trip canceled. So if you cancel one trip, and how much risk you can reduce. Another indicator is the risk reduction per increased hour at home. So if you increase 1 hour at home, and how much risk you can reduce. Well, the higher the value for these 2 indicators, the more cost effectiveness a policy will have. So we look at the low compliance level, which is 30%, also high compliance level, 80%. We find that for both compliance levels, the S2P strategy is the most effective. So that means if we ask people to just cancel their discretionary trips, like their banking, their dining out, their go shopping to the high risk areas and reroute their destinations to low risk areas. So this strategy is the most effective to reduce the transmission risk for the entire study area. So this is the recommendation we give out to the government. Well, through the first 2 studies, we find some limitations of our mobile phone data. For example, it does not cover entire population because it highly relies on the mobile phone use. And we know some senior people and also children, they don't have mobile phone. So they were not covered in our study. And also there's an issue of market share, and our data only cover about 70% or 75% of the market. Another limitation of mobile phone data is it doesn't have any demographic and socioeconomic information for mobile phone users. So everyone is just a number. And we don't know whether this person is a female or male, or which age group, which occupation. Another third limitation is for each trip or each stop of the mobile phone user, we don't know the purpose of that trip. For example, this stop is for dining out, or it's for shopping, or for work, and there's no information. So we tried to address these limitations in our third study, in which we utilized the mobile phone data sets to simulate COVID-19 in the city. So this was published last year. So in this study, we're trying to use a data fusion method to generate the travel trajectories for all individuals in the city. All right, so not only those who have mobile phones, but also for those who do not have mobile phones, we are trying to estimate their travel trajectories. And based on the travel trajectories of all individuals, we can simulate how disease or how the COVID-19 can spread across the city. And then based on which we can explore some control strategies to prevent the disease resurgence if the city is reopening. So I just talk about so we have 3 data sets being used for data fusion. And so mobile phone records, we have about 7.3 million records. The strength is we have a large sample here. We also have detailed travel records for every mobile phone user, but we don't have any social demographic information for them, like their age, their gender. And the second data set is the census. Good thing is it has full coverage of the entire population, and it does have social economic information or social demographic information. But the census data usually doesn't tell you the detailed travel of every individual. The third data set is a travel survey. What good thing is the travel survey do have social economical or demographic data for each participant, and also has detailed travel records for every participant. However, it only has a very small coverage of the total population. So you can see, well, the 3 data sets have their own pros and cons, and they are complementary. So data fusion is a process and trying to merge all input data sets into one, which has the strengths of all inputs. So we're going to actually create a new data set from the 3, so in which we have information of every individual in the city. And not only their social demographic information, but also we have the travel records of everyone. So this is the algorithm of data fusion. I'm going to move talk about this quickly. So we start with using census data to synthesize individuals. So we're going to assign them some demographic features like their age, gender, occupation. And also we group individuals into households and assign them to residential buildings, so they have geographical locations. And also we assign each individual with phone ownership. All right, so based on their gender and age. So some of them will have mobile phones, some of them will not. And then for those who have mobile phones, we are going to link them, we actually link them to a mobile phone derived trajectory. And for those who do not have mobile phone, so we link them to a characteristic travel trajectory derived from the travel survey. So that's how it generates the movement of individuals, of all individuals in the city. So this is a demonstration of how every individual is actually moving around the city. And here is another example of a synthesized household. So this is a synthetic household. We have the geographical location of this household. Also, this household has 1 adult male, 1 adult female, and a male child. So we have their gender, we also have their occupation and their mobile phone ownership. And so this is the simulated travel trajectory of the female adult. And we do differentiate their travel behavior in weekdays and weekend. So as you can see, in the weekends, they're going to stay at home with more time. So this is also the travel trajectory of the simulated children or child, which is basically travel between home and school. All right, so based on the travel trajectories of all individuals, and we could identify where individuals might stay at the same location and during the same time period, so that they could have possible contacts that transmits COVID-19. So for example, people can stay at home during the nighttime, and then they have contact with their household members. And then in the morning, they travel to their workplace. They have contact with coworkers or their classmates in the school. And after school, after work, they may go for shopping, they may go for restaurants or theater. And during the pastime, they may have casual contacts with other visitors at the same place. All right. So based on this context, and then we can start to simulate how COVID-19 may spread. So every individual can have a number, can have a infection or disease status. So all of them will start with a susceptible status, which means they are healthy and they can be infected. And once the susceptible individual has contact with an infectious person, and then there's possibility that this person will become latent, which means you are infected, but you're not infectious yet. And after a few time periods, like a few days, well, the person can become infectious, which means this guy can infect others. And then the infected people can start to show symptoms and then get quarantined. And after a few time periods, get recovered. Or if someone who do not have symptoms but still infectious, and so will remain infectious for time periods and until recovered. So that's how we simulate the transmission of disease. So I'm going to play a video here. Okay, okay. Okay, so this is our simulated transmission of disease. So sorry about Chinese here, but the orange dots represent the people who are infected, who are in a latent status. So they're infected, but they're not infectious yet. And so for those red dots represents the infection or people who start to have symptoms. And the blues are people who get quarantined or being hospitalized. So let me continue playing. Okay. And also we have the epidemic curve here as well. So this is the simulation. So basically, based on this model, because of mobile phone data, we can actually predict where and when each individual in this city can be infected. We did some validation of our model, trying to make sure that it's a solid base for exploring control strategies. So here, where's the point? All right. So the green curve is our simulated number of cases over time, and the orange bars are the CDC reported number of cases over time. So by adjusting some model parameters, we think we have a very good fit to the observed cases. And also trying to match the case distribution by age group. So the green bars are the simulated cases by age group, and the orange bars are observed cases by age group. And we also say there's a good consistency between the spatial distribution of simulated cases versus observed cases. So here each point represents a district in a city. So the x-axis is observed number of cases, and y-axis is the simulated number of cases by different district. And we get a very good correlation coefficient about 0.9. So we believe that model is good. So, and then the question is, what's next? So if the city is about to reopen after March or during the March of 2020, and what may happen? Are we going to have another outbreak? And then what kind of strategies we can use to prevent, to avoid the disease resurgence? So we consider three types of interventions when city is reopened. So which means all business and schools are back to normal. So one intervention is still we use contact tracing. there are different levels. Level 0 means there's no tracing. 1 means we only trace household members. Level 2 means level 1 plus also tracing work group or classmates. Level 3 means level 1 and level 2 plus 50% of casual contacts in public places like restaurants, grocery stores. And level 4 is basically level 1 plus level 2 and also all casual contacts in public places. The second intervention is face mask wearing. We assume that if you wear a face mask, you can prevent infection by 50%. You can reduce the infection by 50%. And also, we assume there is a compliance level of population, especially when the city is reopened. So the compliance level can be ranged from 0 to 100%. And also a self-testing and home quarantine intervention. So if you feel sick, you do a self-test, and if you're positive, you're voluntarily stay at home until you feel better. We also consider a compliance level from 0 to 100%. So we simulated all possible combinations of these interventions over 100 days, and each combination for 1,000 realizations, and trying to reduce the randomness. And for each realization, we estimate the chance of disease resurgence, which means the basic reproductive number is greater than 4 or greater than 1 after 4 weeks. So this is our simulation results. So this chart shows the chance of another outbreak of COVID-19 or the disease resurgence under the combination of 3 interventions. So I have the self-testing and quarantine, and here is the face mask wearing rate. And so different different panels means different levels of contact tracing. So if you can see and also the circles indicates the probability of disease resurgence. So the darker the circle, the higher the chance of another outbreak once the city is reopened. So you can see, well, if there's no contact tracing, it's almost impossible to avoid the second outbreak. It doesn't matter how high the compliance of people with the face masks and with the self-testing. Well, if you can do a contact tracing level 1, which means you start to trace household members, well, there's still so there's still possibility that we can control the chance of disease resurgence under 5%, which is here. And well, if you have more and more efforts on contact tracing, and it's more likely that you're going to avoid the disease resurgence. So while we talk with governments, then they expect that the chance of disease resurgence can be reduced or be limited under 5%. So that is thought as acceptable by the government. So that's why we actually create a contour line of 5% chance of disease resurgence on each panel. So basically, if you see any possible combinations above the contour line, so these are options we can give to the government to avoid another outbreak. And the one we do suggest to the government is actually this one. So it's at the contact tracing level 2, which means we track people in your household and also in your workplace or school. But this is feasible because it's much easier to identify close contacts in households and schools or workplace than identify who you actually met in public places. So that's why we use contact tracing level 2, and with a compliance level of 80% for face masking or face mask wearing. And we think this is feasible in China because in China, usually you can achieve a pretty high compliance rate for face mask wearing. and 40% for self-testing and self-quarantining at home. And we believe that once the city is reopened and people are eager to go outside, they want to go back to work, they want to go back to school. So that's why we choose a lower, relatively lower percentage or lower compliance level for self-testing and self-isolation at home. So we suggest this strategy for not only Shenzhen city, but also possibly other mega cities in China, like Beijing or Shanghai, if they want to rapid suppression of COVID-19 outbreaks. All right, so I think I'm going to stop here and wrap it up. So in the 3 studies I presented here, so we proposed a new framework to use the big phone, mobile phone data to estimate the risks and uncertainty of intra-urban disease transmission, including dengue fever and also COVID-19. So we think with the help of the mobile phone tracking, it's feasible and promising to personalize disease intervention based on people's spatial behavior, like the short message example I gave you. And also using the mobile phone, we can achieve unprecedented level of realism in epidemic modeling and simulation. So as you can see, we can predict when and where for everyone in the city who might get infected. So this model, we think, lays a solid foundation for future precise intervention of the city. So that's all my presentation. Thank you for your time, and questions are welcomed.
Thank Dr. Mao's very interesting presentation about how to use the big mobile phone data to estimate the risk areas of dengue, and also to use the short message to interview the people's travel behaviors. And also use and also simulate the control policies, different control policy scenarios to give for the policy recommendations. So now we open to the questions to see if any questions. So I think it's very interesting. Actually, as sort of this changing people's travel behavior. So I'm wondering, you mentioned is you're changing the travel route since it avoid some like risk areas.
Mm-hmm.
Did you like for the research also suggest like transportation mode, since the transportation mode is also related to some like risk level?
Yes, that's a good idea. I mean, people travel by car and also travel by subways, public transit in the city. Well, the problem is, well, we don't have from the mobile phone data only. We actually don't know which travel mode they're using. That's the problem. We don't have this information. You only know while they dislocate from, while they move from one location to another. But well, you have to guess which travel mode they use possibly based on speeds or something like that.
Yeah.
So the mobile phone data actually doesn't tell you. It only tells you the movements from one location to another. We actually don't know which mode they use. Could be walking if the movement is slow, or if they're fast, it could be by car. But I think there's definitely some future work we can do on trying to add some travel mode information to road trips, and maybe there are some other interventions we can do on that.
It's because of this data it's not provided, or it's because it seems that some apps they try to track your exercise behaviors, so then can actually based on your movement to have I think it's a judgment about your speed. So
Right.
That's
So the data is not derived from the personal, I mean the apps installed on their cell
okay.
phone. It's actually provided by the mobile phone company.
Okay.
So it's not giving it doesn't give you such details about how they actually travel from one location to another.
Okay, so you mean actually the company may have this data, but they not
I don't know,
receive
but I don't know.
release
They may
yet.
have this data. Yeah. Yeah.
Oh, okay. I
Maybe
see.
maybe the apps company have this data.
Okay, I
Yeah.
see.
Yeah.
Kai, could
Mr.
you,
John.
yeah, Kai.
Yeah, hi, Dr. Mao. Yeah, this is a great study. I just have one quick question. So I know you don't have the individual data, right?
We do have the individual mobile phone tracking data.
Okay, so my question is that, I mean, based on individual data, I mean, is that possible to know whether this guy is inside or outside?
No, it's well, it's actually we only know. Am I still sharing the screen?
Yes, yes.
Okay. So actually, we only know the cell phone tower location. All right. So as long as you're in the polygon, and the only information we have is the cell phone tower. So actually, it can be anywhere in this tower. It doesn't matter it's indoor or outdoor. Yeah. So it's we don't know exactly location of that person. The cell phone company doesn't want to share this information because that's very sensitive. So they only give you the information of the cell phone tower. That's the best information we can use to geolocate people.
Okay, I see. Okay. So I mean, for the general people, I mean, so I mean, I just wondering, for example, if you recruit some people for a small study, for example, like the 1,000 people, so you do have their permission to get their mobile phone data. Is that possible for you to know whether they're inside or outside?
Well, if you georeference those points onto, if you have a base map for buildings, I guess yes. Okay, I mean, it's possible. You might even guess actually which floor they're at based on the elevation. So I mean, if you do the personal survey or individual survey, you ask people to share their mobile phone tracking records. Yeah, you can actually differentiate indoor and also outdoor activities.
Okay, yeah, thank you very much. Yeah.
One question from the Fu Zhenying is thank you for the inspiring talk. I'm wondering, in addition to the mobility information provided by mobile phone dataset, can the mobility data also provide information about people's communication pattern? Like who is calling who from where and at what time? Do you think in what way can this communication pattern be useful for the disease control?
I guess the company, I mean the mobile phone company definitely has that data, but they just don't want to share with us for research. I mean, definitely they have the records of who actually called, who is calling whom, from where, because usually, well, when your cell phone is connected to is if you're calling someone and your cell phone is connecting to the cell phone tower, and then you're connected to another person, so the cell phone tower is realized where you are. So I guess definitely the company knows that information, and the problem is how you get that information from the company. So in terms of the second question, do you think in what way can this communication pattern be used for disease control? We haven't thought about yet. I think this information will be very useful for us to infer how people may have physical contacts. Even though we're talking about, let's say, like a virtual contacts through, let's say, mobile phone apps or mobile phone core. I don't know, maybe I think this information can help us to infer how people might connect to each other.
Yeah, I think that's very interesting.
It definitely could help us to, I mean, give us some information about how to group people together. Let's say if mom call a child, so we know, okay, this person might stay in the same household, or if someone is calling a co-worker, and then we can put this two person into the same workplace. So I think this information about how they communicate through cell phone can give us some better source on how to group people into households or into workplaces. Yeah, that's my thought.
And also I want to add is, I think that this question is kind of related to the existing studies, how actually people's virtual contacts will lead to the physical contacts, the probability, how probability the visual contacts will lead to the physical contacts.
Yeah,
so,
exactly. Well, yeah, if they have some virtual contacts, that increase the chance of have physical contacts.
Yeah, I think Zhenyin may check the studies is like currently have studies is already have studies like social media contacts, how the social media contacts will actually affect people's physical in-person contacts.
Yeah.
So yeah, I think have other questions? So I think the other question I have is very interested to see you have different scenarios, policy scenarios for the compliance level. So you show the compliance level is from the 10% to 100%. So then did you have for the results is which one has the highest compliance level for this? I think you have five or six scenarios.
Which study?
You have figure to show a figure is for different restriction level. So which means the one is this one. So for all of these, it's the cancel all trips has the lowest, the highest compliance level.
No, this is compliance level from 10% to 100%.
Okay.
And this is actually the reduced risk. So how much risk you can reduce by different policies and under different compliance level.
Yeah.
So when you have more, so if you have higher compliance level, you can see more and more risk can be reduced.
Yes. So this is the figure is from the real data, or is it from your?
Oh, it's from the simulation results.
Oh, okay.
So we simulate. So basically, we send people this message, and they comply to the message, and then what's results?
Okay, so which means that the bottom one, change departure or arrive time, has the highest compliance level.
No, so this is different compliance level, and actually has the least is the least effective strategy because it doesn't reduce too much risk. So we were trying to implement those strategies so that we can reduce the transmission risk. So you can see if even you have 100% compliance to the temporal strategy, you can at most reduce 10% risk. Does that make sense?
So when you say compliance level, you actually like when you say 100% compliance level, you mean within these communities, all the person.
Right. So all those 310,000 people who we sent message, they comply with the strategy, which means they're going to change their time.
Okay.
So even you have 100% compliance, if you use this strategy, you can only reduce the overall risk by 10%. So that's why we see it's not very effective.
Okay. I see. Okay. For other questions, I just
yeah. Actually, I have a comment on this one.
Okay.
I think the effectiveness evaluation is very important. So if you can, for example, random choose some people to have real data to evaluate this study, that'd be wonderful.
Yeah, well, that's what we're thinking about it. Yeah.
The reason why I ask this, because one of my research areas focus on air quality. I just thinking, probably you can switch this one to air pollution. For example, if we found, for certain hotspots of air pollution, for example, during the morning rush hours, you can send a message to some people, right? You can, maybe you can delay your travel time. Maybe you can take the subway instead of the cars, So I think that'd be very useful. Yeah.
Yeah, that's a good idea. I mean, air pollution will be very similar to mosquito bites.
And also air pollution because it's everywhere, right?
Yeah.
Yeah, especially in the big cities, we can see clearly, the temporal pattern and the hotspots.
That's a good idea.
So, for any other questions? So, I think we already passed the time. Actually, I have some detailed questions, but since it's past the time, so I would think we just stop here, and I would thank Dr. Mao's very interesting and insightful presentation. And usually we give for the applause for the speakers and thank you for great talks. Yeah.
Thank you very much. Thanks for having me.
Thank you.
Have a great day.
You too. Thanks.
Bye-bye. Take care. Hope to see you next year.